In this video, I'm going to show you a graphical method that actually allows us to visualize the information in a differential equation and determine qualitative properties of its solution curves without actually solving it. How are we going to do this? The tool is a diagram called a slope field. I'm going to illustrate this through the example dy dx is equal to negative y. What is this differential equation telling us about the geometry of the solution curves? Well, we can think of this differential equation as telling us the slopes of all the tangent lines to every solution curve. For example, consider the point 0, 1. The slope of a solution curve through this point has slope negative 1. And the way we encapsulate this in a diagram is to draw a short line segment at the point 0, 1 with slope negative 1. And we continue to find the slopes of tangent lines, and we draw a short line segment with the slope given by the value of y prime at all points x, y. Well, not really all points, because that would be crazy. Instead, we try to be systematic about it and find the slopes at all points on a grid. So I'm going to make a grid, and then I'll fill in the slopes at all of my grid points. So let's start at the origin. At the point 0, 0, the slope is 0. So I'll draw a horizontal line segment at 0, 0. And in fact, for any point along the x-axis, the y value is 0. So the slope is 0 there also. So I'll draw horizontal line segments at every grid point along the x-axis. We've also seen that at 0, 1, the solution curve has a slope negative 1. And this is true for all of the grid points whose y value is 1. That is 0, 1, 1, 1, 2, 1, negative 1, 1, etc. So I can draw a line segment of slope negative 1 at all of these points. At the point 0, 2, the slope is negative 2. And the slope is negative 2 for all grid points with y-coordinate 2. Let's look at the point 0, negative 1. Here the slope is going to be positive 1. And the trend continues for all the points along the line y equals negative 1. Slowly, we can fill in the slopes at all of these grid points. And what we get, we call a slope field. This is a diagram that shows the slope of the tangent to a solution curve. Now we can actually sketch some curves to get a general sense of the behavior. The solution curve is a curve that is tangent to the slope field at all points. For example, if we start at 0, 0, the curve will just continue along the x-axis. A curve that starts above the x-axis is going to swoop down until it becomes parallel with the x-axis. We get the opposite behavior for curves whose initial value is below the x-axis. They move up and curve until they become parallel with the x-axis from below. So just by drawing this slope field, we can tell qualitatively that all solution curves are going to tend towards y equals 0 as x gets large. Note that this differential equation dy dx is equal to negative y is actually separable. And the family of solutions is given by the curves y is equal to c times e to the negative x. But we were able to sketch out the general behavior without knowing these functions. This behavior of this particular differential equation is often called exponential decay because of the way all the solution curves decay to 0 along exponential functions. So why am I teaching you about slope fields, especially since they're so tedious to draw by hand? Well, in practice, we have a machine draw the slope field for us. And while slope fields are qualitative rather than quantitative, we can find a slope field for any first-order differential equation, even if it's not separable. In fact, The next problem asks you to find the slope field for a differential equation that is not separable, so you wouldn't be able to solve it otherwise. So it's definitely worth the effort to get familiar with the process of drawing slope fields, as well as determining qualitative features of solutions from slope fields. I hope you'll enjoy it.